1.3. This is our second time presenting it to the world. My name is Sean Parkinson, as Kristen said, a senior software engineer at WolfSSL, and today I'll be talking about TLS 1.3, what is it and why you should be using it. This presentation is slightly different to last time as the standard has been finalised, and I'll be taking a little time to talk about the current state of play. So I'll first give an introduction of what TLS 1.3 is and some of the features. Next, the advantages of using TLS 1.3 over TLS 1.2, particularly the performance and security features that make it attractive. After that, I'll discuss the status of the standard. After the many years of development, are you ready to go in real world? Finally, I'll tell you how to use TLS 1.3 with WolfSSL, discussing a few of the APIs for the new features as well. So TLS 1.3 is the newest version of the SSL TLS protocol, which is the standard for securing communications over TCP/IP. The standards document was in development for over 4 years, but is now complete. A lot has changed from TLS 1.2. Many new ideas about how to improve the security and performance of the protocol has resulted in the format of nearly every single handshake message changing and some new messages being added as well. Now let's look at some of the new features. One of the more important changes has been how TLS performance resumption. The old mechanism of sending a session ID requires a server to store state and has been part of many vulnerabilities. Instead, in TLS 1.3, resuming a session is performed with a session ticket. Session ticket was an extension to TLS 1.2, but now is the only way to resume. The session ticket contains an encrypted copy of the state of the previous handshake. Therefore, only servers with the encryption key can resume sessions. Alternatively, pre-shared keys can be used with the same messages to establish a connection. Another significant change to resumption is that by default, a key exchange will be performed doing EDH or EC Diffie-Hellman to create a shared secret ensures forward secrecy. This is a cost, but it is important to the overall security of the handshake. A new and controversial feature of the TLS 1.3 is the zero round trip time handshake with early data. This handshake has the client sending application data protected by a key derived from the previous session with the client hello. This means you can get small amounts of data from the client immediately in the first round, rather than waiting for the handshake to complete. There are security issues with this feature though. As the same key and IV are used each time, the one from the previous session, there is no forward security and therefore a risk of replay attacks. Another new feature is post-handshake authentication. This refers to client authentication using certificates. If a client is connecting to a website where some of the pages need authentication and others don't, the server may delay client auth until after it has seen the URI request. That is, the client auth happens post-handshake. Also, for long-term connections like VPNs, the keys and IVs can be updated post-handshake using new handshake messages. This is not a feature that is expected to be commonly used, but a connection that has been open for a day or has had hundreds of megabytes sent across should be rekeyed. This is done by requesting a key and IV update. Now let's take a look at the advantages of using TLS 1.3 over 1.2. There are two major reasons. TLS 1.3 is more secure and it has fewer round trips in the handshake, which means a faster negotiation. Let's start with security. Only secure Cipher suites have been included in the standard. This is actually a little misleading, and I'll get back to that later in the slides. But in essence, when performing a full handshake, you must perform a Diffie-Hellman style key exchange. This ensures perfect forward security. That is, each handshake is protected by a unique secret based on the key exchange secret, known only to the client and server. Many groups were not happy about this, as it makes monitoring of networks harder. Many email chains went around about this on the working group mailing list, but it was finally agreed that the standard must not be weakened for interception. The dangers of abuse or accidentally reducing security are just too great. Updates to the TLS 1.3 standard are being written in other standards groups to allow man-in-the-middle style monitoring, but they will not be recognised by the IETF. Another security improvement has been to encrypt all handshake messages after the server hello. The key and IV used for encryption are based on the key exchange secret and therefore secure. So protecting all the information that is used to negotiate the handshake, or as much as you can, is a great improvement to security. Next is that resumption has been redone, as I've gone into before. The key derivation algorithms have also been updated. Previously, the key derivation function was designed by those writing SSL TLS and didn't have a security proof. TLS 1.3 now uses a standardized function that is both an RFC and a NIST standard, and it's known as HKDF or HMAC KDF. Finally, RSA PSS is being used for signatures in the handshake. In the past, RSA PKCS 1.5 signatures have been used and are still in use with certificates for the foreseeable future. RSA PSS has a security proof and is more secure against attacks. This is a welcome change given the number of Blankenbacker attacks in the past. Performance. There are fewer round trips in a full handshake, which is a good thing. In detail, the key exchange is performed in one round trip in TLS 1.3. The client hello contains the client's public key, the key exchange public key. The server creates its own key pair and secret and sends back the public key. In fact, the server now sends all the information to complete the handshake and can even send application data, all in the server's first flight. The client then calculates the secret and finishes the handshake, sending back application data. Compare this to TLS 1.2. The client hello is sent, the server creates a key pair, key exchange, and sends the server's public key. The client creates a key pair and calculates the secret and returns its public key. This is a whole half round trip slower. The application data is now sent in the next server flight, a whole round trip behind TLS 1.3. This is a performance gain for TLS 1.3, especially in high latency networks. A further faster handshake is the zero round trip time handshake, zero RTT, where the data is sent with the client hello as a separate application layer message and encrypted with a key derived from the previous session. To be able to get small amounts of data immediately is great for embedded systems like sensors. Okay, so what is the status of the TLS 1.3 specification? The TLS 1.3 specification has been finished, has been finalized, and is designated as RFC 8446 back in August 2018. So the whole process took about 4 or 5 months from the time of the final draft, but it got there in the end. Since then, there has been a number of companies advertising their support. In particular, web browsers like Chrome, Firefox, and Opera support the RFC version of TLS 1.3 by default. That's the final version with the latest version of the protocol. Other browsers like Apple's and Microsoft's don't have that final draft support and don't have draft support on by default for good reason. It needs to have a corresponding draft version supported in the server, and typically you've only got one version of TLS 1.3 built in, and that will be the final one. Given that common browsers support TLS 1.3, then it's clear that there are web servers out there that support TLS 1.3 as well. There are articles on the web explaining how to compile up and configure Apache and Nginx to use TLS 1.3. The January report of SSL Labs, SSL Pulse reports that 10.7% of surveyed servers are able to support TLS 1.3, and that's the final version of TLS 1.3. While everyone is pushing forward to support the RFC or final draft, it is worth looking back at the old drafts and where they fit in. So the last draft version was draft 28, which is no different from the RFC apart from minor edits. There hasn't been any wire format changes since draft 25, and so any client or server supporting these versions are going to be able to support the RFC. The only wire difference to the RFC is the version number of the protocol, which is now hex 0304, as opposed to the 7F and the draft version number. This has to be advertised, the version number of the protocol, and only those that support those particular versions will be able to interoperate. Older tested versions were draft 22, 23, which came out after interoperability changes, and further back is draft 18. These need reciprocal versions to work with, and going forward should not be used. So now I'll tell you about using TLS 1.3 in wolfSSL. As just mentioned, there are various versions floating around out there. wolfSSL supports the RFC version by default, but can also support others. The code can be figured to support older versions like 22 or 23 if that is required. But don't do that. Update both sides to the RFC version as soon as possible. So what do you need to change in your application to use TLS 1.3? Well, nothing. If you use the wolfSSL v23 client and server methods, they will negotiate the highest supported protocol in the client and server. If you wanted to just use TLS 1.3, then you have to use the wolfSSL v13 client and server methods when creating a wolfSSL context, just as you would use wolfTLS v12 if you wanted to use just 1.2. Note also that the default configuration of wolfSSL does not include TLS 1.3. So that means that you need to enable this if you have the space for it. At the recent yearly review meeting, we've decided to enable it by default in the next release. So you won't have to add it to the configuration line or add it to your user settings. Now, Cipher suites have changed a bit, as I talked about earlier. Previously in TLS 1.2, the Cipher suite included the key exchange and authentication algorithm. This is no longer the case. As the client's key is sent in the client hello, and thus the negotiation of key exchange algorithm happens separately, and while they're at it, they pull out the authentication algorithm as well as PSK, and they're negotiating the client hello too. So the new Cipher suites are as listed. There are only 5 at this time. 2 are using AES GCM of different strengths. CHAD 20 poly135 is a backup if AES GCM has an attack found on it. Though the CHAD 20 poly135 can be faster on processors that don't have hardware support, like built-in instructions using AES GCM. Also, if you don't have the built-in instructions, then there can be side channel attacks on AES GCM. Also, AES CCM was included for embedded systems, as it's been popular in standards for that. These are the strings that you pass in when setting the Cipher suites for TLS, which means they're completely different and you need to set them separately, or you can use all of them by default. One major change is that you want to support, if you want to support resumption, then you'll need to implement a callback that encrypts and decrypts a session ticket in the application. To set the callback, use wolfSSL context set ticket inc callback. There is a good example of how to do this in the example server and test.h files in the wolfSSL source tree. It's important feature, the session tickets, and so this is probably going to be needed. What the algorithms you need to use typically is going to be a streaming cipher, so that can be, say, AES GCM if that's what you're using for the handshake, or poly1305, CHAD 20 with poly1305 maybe. Next is the early data. As early data has a different security profile as compared to normal application data, special APIs are provided to read and write it. Only the client can write data, and client applications use the API wolfSSL write early data. So this is an opportunity for the client to provide a little bit of data to the server using the previous session's secrets. So they can write some data with this API, and the servers must use the wolfSSL read early data to receive it. And if the client doesn't send any, then that's okay. It doesn't matter that the server called read early data. The API will return no data, and you can continue on with the handshake as normal. To limit risk, you can set the maximum amount of early data in the establishing session using wolfSSL set max early data. So this information is included with the session ticket in the previous handshake, and the server will then know how much data it should read. Any data after that will just be ignored. It will just drop it, and it won't cause any errors. It will just ignore it. Other APIs for other features. Using ephemeral TP-Hellman with pre-shared keys is the default behavior, which is there for security. Make sure that there's a forward secrecy. But this can be turned off on the client using wolfSSL context, no DHE PSK. An extension will be sent in the client hello as per the standard, and the server can choose not to perform the key exchange. So it's still up to the server to choose not to do that. This makes sense in very limited environments where public key algorithms are too costly. So if it's an embedded system with low power, limited computing capacity, limited memory, then perhaps you'll want to do this. It's still secure in terms of it's using a pre-shared key, a pre-shared secret, but there's risk that the risk is that once the key has been exposed, for whatever reason, if the device has been hacked, then all the communications that have been protected by that key will be exposed, or be able to be read anyway. So post-handshake authentication is allowed on the client side with wolfSSL context allow post-handshake auth, and is requested after the handshake on the server with wolfSSL request certificate. So yes, you have to explicitly allow it on the client side. Key share is an extension sent in the client hello and returned in the server hello containing the public key for key exchange. To use a hello retry request instead to negotiate which key exchange algorithm to use rather than jetting one or more up front, then you call wolfSSL no key share in the client. So this means that there's no keys generated before the handshake starts, and only one will be generated at the time the client receives the hello retry request, where the choice of key exchange has been made by the server and described. By default, key pairs will be generated for you. So whichever algorithms are being allowed, they will, the wolfSSL toolkit will generate key pairs up front in the client. To have the key pair for the algorithms you want generated and sent, then call wolfSSL use key share in the client. Only the algorithm or algorithms you specified will be sent. If the server doesn't like any of these, though, then that's okay. There are other algorithms in common, but there are other algorithms in common, then it will respond with a hello retry request, and the client will send a new client hello and generate the, the key pair at that time. A cookie can be sent by the hello retry request to protect against replay attacks using the API wolfSSL send HR cookies. So that's probably useful. A little extra protection if you know you're going to use hello retry request. Also, a call to wolfSSL use key share in the server can be made, and it can improve performance. So if the key exchange algorithm to be used between server and clients is always the same, then pre-generating the key can save time, which would otherwise be spent waiting for a new connection. I did some performance analysis of comparing TLS 1.2 and 1.3 and found that, yes, this does actually help. If you're having a server continuously in loop, waiting for connections and then dealing with them, it does actually turn out that there is time there for the key pair generation to happen in between connections. Finally, the keys and IVs can be updated post-handshake at any time with a call to wolfSSL update keys.
Sean, there's a question.
Yep.
How do you prevent the use of zero RTT?
Okay, so if you do not call on the server read data, then those application messages will be ignored. Does that answer the question?
Let's assume so, unless we hear different.
Sure.
Thank you for answering.
Okay, so in summary, RFC 8446 was released in August 2018, and common browsers have support on by default. Also, some web servers can be compiled and configured to have support, and they're in production at the moment. The full handshake is faster, as the key exchange only requires one round trip to complete. As a protocol, TLS 1.3 is more secure due to the removal of less secure Cipher suites and algorithms, and the introduction of new better algorithms like the HKDF, and also using RSA PSS. To use TLS 1.3 with wolfSSL, then simply add it to your configuration and it will downgrade from TLS 1.3 to the lowest version you support, which should be TLS 1.2 or maybe 1.1. Just on that, note that the browsers are deprecating the use of TLS 1.0 and 1.1 this year, and next year, in 2020, first half, sometime around there, the Chrome and Mozilla have said that they will be removing support for TLS 1.0 and 1.1. So it's a clear indication that if companies like that are doing it, where there's still a lot of servers out there supporting TLS 1.0 and 1.1, that it should not be being used. Should not be, if you're looking to remove that from your support in your products, especially if they're going to be deployed and out there for a long time. Now's the time to go to 1.2 exclusively and stay and look at putting 1.3 in there, because 1.3 is going to be the future. There's lots of good reasons for people to using 1.3 with the security improvements and the faster handshake. So servers will be going over to that rather quickly because it's easy to do and it works better. Okay, so that's it for the slides. Are there any questions?
Let's see here. What third-party SSL 1.3 products do you use in testing? For example, to test against wolfSSL 1.3, Chrome, Firefox, or any others?
So I've done interop testing with Chrome, with Firefox, NSS's server. There's been some boxes out there that I've done draft support, but I haven't actually, I can remember done actual interop testing with the final release version, which is something that's on my list to do. Yeah, and OpenSSL, of course, on the server and client. We've interop tested with that with as many different configuration options as possible. It's important that we do this. We've had customers come back to us to say, other customers, I should say, come back to us with requests to, does this configuration work and things like that. And in the past, we've made improvements to the code base to make sure that we are interoperating with as many known final implementations as possible.
Okay, when will wolfSSL add support for DTLS 1.3?
DTLS 1.3 hasn't come out yet. It is still a draft. We don't have, it's on our list of things to look at this year to see when we'll do it. It is, for us, it's going to be adding in the extra code to the new TLS 1.3 code base to support TLS 1.3. So it's not just a, it's already there, almost working. It is some work to do. But, as customer demands come in, we can accelerate that process, of course. But maybe this year.
Great, thank you. Okay. Was there any impact on memory requirements to support the 1.3?
I did some memory usage statistics on that, and having TLS 1.2 and 1.3, which I thought was the most common use case, it does add a small amount of extra memory usage, direct memory usage, which is expected. There's extra features in there, and that means there's extra fields that have to go in. Different extensions being added means there's extra data that needs to be kept for those extensions, specifically like the key share. So if we pre-generate the key share up front, the TLS 1.3, then we have to store the public and private key. So if you're using, an ECC algorithm for the key exchange, which is typically being done these days, then that's an extra, maybe 92 bytes or something like that. So it's not much more. I think maybe 200, 300 bytes more during the handshake is needed. And so it's very small, but that's as expected. It doesn't really impact things that much. Just a note on.
And then, sorry, go ahead, Sean.
I'll just get in here with my little rant about Diffie-Hellman. So Diffie-Hellman, you shouldn't be really using that if you are on the client side, for the client side reasons, I should say. If you're heading up a public server. These days, there's been attacks that have come out about how to attacks where the server is sending bad Diffie-Hellman parameters, and that means that you should be doing validation of the parameters, and doing that takes a lot of time in a normal world. So people are going to the EC Diffie-Hellman key exchange, which is great. It's less amount of data being sent across the packet across the wire as well. Sorry, and it's faster. Especially if you use a 2048-bit Diffie-Hellman key exchange. And yeah, so look at using ECDH, ephemeral EC Diffie-Hellman in the future. Next question, thanks.
Sure, and just a reminder, if you'd like to ask a question directly, feel free to raise your hand and I will unmute you. I guess it was a follow-up. You may have actually answered this, but can you reduce the memory footprint by limiting support to 1.3?
It does reduce it a little bit, but it's not very significant at all. There's still pretty much the same fields going in for TLS 1.2 and 1.3, and TLS 1.3 adds a little bit. So yeah, it's not significant.
Okay, thank you. Any comment as to memory requirements for TLS 1.3 as compared to TLS 1.2?
We'll need more code. There will be more code there. The TLS 1.3 is a separate implementation of handling each packet. So it's not like it's built into the TLS 1.2 and just adds a little bit more extra space. It is a whole separate thing, but there's some of the more expensive in terms of code space operations like handling certificates is in common with TLS 1.2, so that doesn't it doesn't hurt. There's different extensions, new extensions, so that adds more to the code space. So yeah, the stack and memory usage doesn't greatly get increased.
Okay, another question here. Encrypted with key derived in last session. How is first session handled?
So you cannot do pre-shared key. Yeah, sorry. Yeah, you have to do a full handshake first in order to create the keys to do early data and things like that. So you have to do a full handshake at some point in order to establish trust. Does that answer your question? Okay.
Okay.
Next question.
Yes, the question was answered. Thanks, Sean.
Okay, great. Thanks.
Is EDDSA supported already in Wolf SSL?
So we do have support for the Edwards curve signatures. And it is in the TLS 1.2 and 1.3. Though the whole certificate format thing is still an issue. There's no sort of clear guidelines as to what that should look like, and people aren't really, companies aren't actually issuing certificates for that. So yes, you can use use Curve 25519 for both the key exchange and the certificates, and we can, we interoperate with OpenSSL on that, but it's not a common thing to have these yet. So it does save space in terms of memory usage using Curve 25519 for the whole thing. Though we do have an implementation of the maths, which we call single precision, SP, that is specifically designed to be small code or fast, and to use small amounts of memory in either situation, and it does reduce it down significantly. So it may be that you use 9K when you set the right configuration options for the Curve 25519 handshake, but with the SP and using P2D6, it may be 11 or 12K. So it's still quite frugal in its use of memory when you're using those configuration options.
Okay, I don't see any other questions at this time. If you do have a question following the webinar, you can feel free to email us at info@wolfssl.com, and we will be sure to get that answered as quickly as we can. We can hang out here for a little bit just to see if there's any other questions.
Sure.
Okay, I think I don't see any other questions coming through, Sean. So thanks so much for the presentation.
Thank you.
Oh,
Thank you.
wait, hang on 1 second.
Oh.
We've got a question coming through, I believe. Okay, where will crypto offload cards play a role in TLS 1.3? In the handshake or in the stream cipher?
Using it in the stream cipher can be a little problematic due to the fact that you need to send lots of data across a bus to the card to be encrypted, which is a very fast operation, to be come back again. The most clear advantage is to have the public key operations being done with the device, the crypto offload. Having said that, though, that if you want to keep all the secrets private, then you want to have all of the secrets being generated on the device, and therefore the secret will be in the encryption secret will be in the device to do the encryption of the application data. So, to my mind, the most clear reason to use the device is for the RSA or the ECC operations.
Okay, thanks, Sean. I think with that, we can wrap up the webinar. Again, just send any additional questions to info@wolfssl.com. And don't forget to follow us on Twitter @wolfssl. Thank you, Sean.
Thank you.
And thanks, everyone, for joining.
Thanks for the questions.